My name is Ganesan Subramanian, and my co-author is Neil Nilmegam, and we'll be talking about the heat island mitigation strategy for urban areas using phase change materials. The outline of my talk is first discuss what the heat island effect is, how phase change materials work, and what are the characteristics of these materials that we need for them to work as we intend to. What are the different PCM types, and how do we measure experimentally the properties of these PCMs that we need in order to pick the right PCM, and how do we incorporate the PCMs into the building envelope, and what are the parameters influencing the PCM performance in order to choose the right PCM. And in addition, we need modeling tools for choosing the right PCM. And we go on to discuss the heat island effect, which is the local weather conditions that are caused by the concentration of buildings, roadways, industries in urban areas. Because of these factors that cause the local weather to be extreme, in contrast to surrounding rural areas. Now, this effect is called the heat island effect, and by extremes in weather, we mean flooding type rainfall and heat waves and so on. And here we know that this happens even without taking into account the global climate change that's been happening over the past decades. Global climate change accentuates this effect further. Now, the mitigation of the heat island effect has been demonstrated and to some extent implemented through the use of shade and materials that alter the reflectance and emissivity of surfaces impacted by the solar radiation. Now, considering that building and road construction and operation accounted for the largest share of both global final energy use, it's about 36%, and the similar percentage for the carbon dioxide emission in 2018. So it's in our interest to mitigate the heat island effect in order to reduce the energy use as well as the carbon dioxide emission. Now, here we show that or review how further extensive mitigation is possible by use of phase change materials in buildings and roadways. PCMs are materials that absorb or emit heat at constant temperature at a phase change or a phase transition. Now, in this talk for building application, we usually talk mainly about the solid liquid phase transition. Now, how do PCMs work in energy storage and release? Basically, PCMs are similar to a battery in terms of storing energy. Now, the left chart shows basically the temperature versus enthalpy of heat, and how there is a large amount of heat compared to the sensible heat that's emitted or absorbed at a constant temperature. Now, this is the fundamental principle. And on the diagram on the right shows how during the day the PCMs absorb heat and the transition from solid to liquid. And in the night, when it's getting cooler, the PCM rejects heat and returns to a solid state. Now, the diagram at the left bottom shows the emerging applications of PCM across many range of temperatures and the range of types of materials used. And it has been very popular already to use PCMs in power electronics or electric vehicles for cooling. And in addition for consumer electronics, where the tight packing of semiconductors generates a lot of heat that has got to be removed effectively. And it's also used in biomedical devices, electric storage. And for the talk of interest, we are focusing on building. When you see that the temperature range is roughly in the say 10 to 25 or 10 to 30 degrees Celsius range. And the right chart shows how different types of materials fit into these temperature ranges in terms of their melting points. And so you have gas hydrates, and of course water is there. You takes paraffins, sugar alcohol, salts, and their eutectic property. And we'll look at all the properties of these different types of materials in order to decide what kind of PCM should be used for building materials. Now, what are the ideal characteristics of a PCM? Now, there are 4 kinds of properties: thermodynamic properties, chemical properties, kinetic properties, and technical and economical properties. Thermodynamic properties are the transition temperature, where what is the operating temperature range, what is the thermal comfort requirement, and it should operate close to the average room temperature, and should have good thermal conductivity for energy storage application, and we want low thermal conductivity for thermal insulation application. Now we need a high latent heat of fusion compared to the sensible heat storage, and for which you need a higher specific heat capacity, and you need physical stability with small volume changes. And you need consistent melting and freezing behavior. That is, there should be no hysteresis. What are the chemical properties? You need the materials that are used to be stable for long term, and they shouldn't degrade after many cycles. And you should really need a complete reversible melting and freezing cycle. It should be non-corrosive, non-flammable, non-explosive, non-toxic. What are the kinetic properties? That is the supercooling. You shouldn't have any or little supercooling. And what happens is that if you do supercool, you're not in the right state to solidify and release the heat. And in addition, you need high crystallization rate. The technical and economic properties are that it should be, in terms of applicability, simplicity, effectiveness, it should be compatible with other building materials. Compactness, viability, and reliability should be available in large scale, and most important, effective, low cost. So we want to discuss what are these different types of PCM. Here we show organics, paraffin wax, for example, fatty acids and vegetable oils. And then inorganic salt hydrates and eutectics. Now the advantages and disadvantages are enumerated here. And the advantages are organics are available in a wide range, temperature range, high heat of fusion, no subcooling, no segregation, stable after many cycles, chemically and physically stable, compatibility with a wide range of containers that hold the PCM. And the corrosiveness of the material is low, environmentally safe, non-reactive, and they are recyclable. Now, what are the disadvantages? They have low thermal conductivity, large volume change during phase transition, except for some fatty acids, are unstable at high temperatures, no sharp phase transition, non-compatible with plastic containers sometimes, costly in pure form, low enthalpy, flammable, sometimes different toxicity levels. And many of these things are disadvantages are overcome by using composites, as we later show. Now, the inorganics have some salt hydrates, have high thermal storage capacity, good thermal conductivity, low cost, available easily, sharp melting points, low vapor pressure, and non-flammable. But they do show subcooling, considerable change in volume, sometimes, show phase segregation, and they are incompatible with metallic containers. Now, the eutectics, by contrast, have very sharp melting points and boiling points, high volumetric storage density, but they are expensive. There's limited data available for thermophysical properties. And what are in addition to actually the characteristics themselves, we need to know the types of thermal storage systems before using PCM, because that will aid in our choice of the right PCM. So we divide this into three categories: passive, free cooling, and active cooling. Passive is where PCMs are incorporated into the building envelope to increase thermal mass without any external energy source. Now, this is the most economical category, but has a disadvantage of the PCM not solidifying completely. Free cooling is a technique based on natural nighttime ventilation to dissipate PCM's stored energy, and it's based on natural convection, where during the daytime, indoor air circulates through the PCM unit, and the PCM melts by absorbing heat from the indoor air, reducing the room temperature. During nighttime, when outdoor temperature is less than the indoor temperature, cold ambient air is circulated through the PCM, releasing stored heat and solidifying. The first part is really the passive part, and the other part is the natural convection part when we do the solidifying. System will work only for the right temperature range of the diurnal temperature in terms of the right phase transition mechanism going into play. Now, here there is no external energy source, and that comes to the next category, that's active cooling. It uses fans and pumps to transfer energy to working fluids like air or water. In active application systems, the storage capacity of PCM is typically integrated into the HVAC systems, such as solar heat pumps, air conditioning units, floor heating, and thermal active ceiling panels. And we'll show how a PCM embedded air conditioning unit operates in the in the next slides. Now, the chart here basically shows the mechanism of how the storage system works. For example, in the passive case, here we compare the temperature profile without PCM, that's the red curve, and the temperature profile with PCM, which is the blue curve. And the important thing to notice is the less temperature fluctuation for the PCM case, and the peak is also reduced. And this is how basically the energy load is optimized to be less overall. Now, what are the parameters influencing the optimum PCM placement in applications? Now, this is very crucial in really picking the right PCM as well. So there are the optimum position, the position that provides adequate heatings for the PCM to fully melt during the daytime. then adequate cooling in order for them to fully freeze during the nighttime. Many parameters might influence this process, and we categorize them into external and internal parameters. Now, the external parameters are the climate and weather and the application target. The climate and weather, hot or cold regions, summer or winter season. And here the application target is how do we want to use and store and reuse the heat. Let's reduce the heating load. Different applications would have different kinds of application targets. And or do we want to reduce the internal or external heat gain? That is to remove the heat and reduce the cooling load. Or do we want to store energy during low rate periods and use them during high rate periods? And the indoor environment, in fact, the parameters are, do we want to use mechanical cooling and or heating, or do we want free cooling like the natural convection mechanism we discussed earlier, or do we need all day, night mechanical ventilation? Now, this will influence the placement. For example, if you're using an air conditioning type system, we might need a ceiling to have PCM. Now, how are the walls orientated? What are the wall materials? You need high thermal resistance for insulation to hold the heat, or do we need low thermal resistance, like concrete, bricks, etc., so that you don't waste the heat? Now, the internal parameters are related to the PCM thermal properties and the quantity and layer thickness. The melting and freezing point, the heat of fusion, thermal conductivity, specific heat capacity that we discussed earlier, and in addition, this should include the density. And then we need to know the layer thickness and the amount of PCM we are using in order to, which will also influence the placement. Now we discussed how do we really incorporate PCMs into the building envelope. Now the PCMs can be of different types. They could be panels, they could be bricks, and it could be a slab or a pouch or a blade or a slat, or it could be spheres or tubes. And these are the different kind of containers. And how do we incorporate these? One is, for example, it's a direct incorporation. This is added directly to the construction material, such as gypsum or mortar. Or you could, construction material is immersed into the liquid PCM and it's absorbed due to capillary action. Or you could encapsulate it, micro or macro, by covering the PCM with a shell for protection from the outside environment, as well as for leakage prevention. And then you go on to a little more sophisticated method where the PCM is contained in a carrier matrix so that it's stabilized in terms of shape, or you could stabilize it in terms of form, where using a composite material, you retain the maximum amount of one or more type PCM, showing no leakage at melting temperatures. And obviously, these different types would have would be picked based on the application or the area of the building that you want to cover. The diagram on the right, for example, shows how the PCM is incorporated into the wall board. And I must mention here that for buildings, a very large amount of PCM is really in the wall boards. Now here is an active application active mode application of PCM in an air conditioning scheme. And the chart A shows where the PCM sits in terms of the overall scheme, where you have an evaporator and a condenser, and a compressor, which is part of any air conditioning system, and how we control the circulation of the air into the PCM bed. Now the chart C shows just one piece of it, where the return air, which is higher temperature, return air from the buildings, passes through the bed and cools to 20 degrees. And this is in turn combined with the ambient air fed to the evaporator. This effectively reduces the cooling load, then the cooled air supplied to the room. In the charging mode, in this diagram here, the supply air from the evaporator is bypassed through the PCM bed, allowing it to freeze. So it's an optimal combination of everything. Now, how do we determine experimentally for measuring PCMs, for measuring physical properties like specific heat of density, thermal conductivity, and density? And experimental methods are needed very much because of the complex nature of most PCMs. And common methods are conventional calorimetry, differential thermal analysis, and differential scanning calorimetry. The disadvantage of these methods are requirements of small sample sizes that do not reflect the properties of the actual bulk material that they're going to use in practice in the building, the equipment complexity. And we cannot measure several samples simultaneously. And in addition, we can't really observe how the phase change process in the PCM is going when using these methods. Now, there's a new method that's developed to overcome these disadvantages of determining melting point, degree of supercooling, heat of fusion, specific heat, and thermal conductivity of several PCM samples in parallel. The basic principle is to log the temperature change of the PCM in the tube when you impose a sudden temperature change in the surroundings. The heat transfer between the PCM and the surroundings is determined from a twin set of samples with known properties. And this is especially useful if you have all these different samples or different types of PCM, for example, and you want to pick the right one. And you can do all this simultaneously. Now, given that we have the properties of the PCM, physical properties, and we are more or less certain about the kind of application in the building in terms of using wall boards or basic infrastructure of the building envelope. There are several tools available for modeling of the PCM enhanced building envelope, even before we apply physically into the building. And this diagram shows over a wide scale range from all the way from material design to the final product through device design, the science and the engineering involved. So if you're looking at just the PCM properties, and say, for example, you want to look at, say, supercooling, you might look at it at a quantum mechanical level or a statistical mechanical level or a mesoscale physics, or in terms of when you go to the continuum mechanics, when you go to the device design. And in the material design, the various tools are the DFT, that is the density functional transforms. And you can use molecular dynamics, Monte Carlo methods, then the various AI tools to design the right type of materials from scratch. And then you have various experiments for characterization. And when you go to the device design, you can have tools that use effective medium theory or basic material and energy balances, like the finite element methods, finite volume methods, system simulation, and again, artificial intelligence. These are tools like ANSYS, and then there are many tools available at the Department of Energy websites. And all the way to the final product and system. And this reflects then there would be experiments at the manufacturing scale-up and automation level. Now, for modeling at the building scale level, a new method has been developed for choosing the best PCB. And here it involves picking a different set of variables, and this approach seems to be promising. In the traditional approach, the unknowns are climate information, building geometry, building envelope materials with known thermal properties like specific heat and thermal conductivity, the air exchange rate, and the thermal disturbance. Now we need to find the indoor air temperature and the heat loads, etc. And the traditional approach requires really an iterative approach in terms of picking the right materials. So the new approach basically puts these iterations into the modeling, where now we know climate information, Q, building geometry, thermal comfort demand. Now we need to find building envelope materials with ideal thermophysical properties, which can be a function of temperature, the optimized heat load, the minimal heat load, the optimized exchange rates. And so we are basically turning this thing inside out to avoid the iteration. So this review has discussed, conclusions are basically that the PCMs are an inexpensive means of mitigating the heat island effect that has been exacerbated in recent times due to climate change. Now, advances in micro and macro encapsulation techniques have made incorporation of PCM into building infrastructure practical and economical. Now, as I showed in the last chart, there are extensive research and development opportunities for material scientists and engineers from the material design stage through the device design to the product and development. Thank you.